Hi, my name is Damien, and today I'll be presenting on my medical electronics assignment on biomedical signal processing system. This is designed to amplify and clean the heartbeat signals that are captured from a stethoscope's acoustic output. The system picks up the sound via a microphone, then processes the signal through multiple amplifiers and filter stages. Then, it drives a speaker with an output power of 0.5 watt and 8 ohms to broadcast the heartbeat sound. The signal processing system consists of 4 main stages, each being responsible for a specific function. Firstly, the preamplifier, followed by inverting amplifier with adjustable gain, then active low pass filter, and lastly, voltage follower plus audio amplifier. So here is the schematic diagram that was given to us. And this is the patch circuit that was done by me. The first stage of this system is a preamplifier, designed to amplify the very weak heartbeat signals detected by the microphone to a level suitable for further processing. The operational amplifier is the IC TL072, a dual low noise JFET input op amp. It is configured as a non-inverting amplifier with fixed gain, providing high input impedance and low noise, ideal for weak biomedical signals like heart sounds. At the input C1, a 10 microfarad coupling capacitor blocks the DC bias from the microphone while allowing the AC heartbeat signal to enter the op amp. A voltage divider made up of R5 and R6 biases the input to meet supply at 4.5 volt. This is necessary because the op amp operates on a single 9 volt supply and cannot process negative voltages. Without this biasing, the negative half of the waveform would be deep clipped. Centering the signal at 4.5 volt allows for symmetrical amplification, preserving the full shape of the heartbeat waveform. The gain of this amplifier stage is set using R2 and R3, calculated using the formulas. Gain equals 1 plus R2 over R3 equals to 1 plus 220 kilo ohms over 10 kilo ohms equals to 23. In addition to amplification, this stage also provides frequency filtering through a combination of R2, R3, C2, and C3, forming what's known as a bandpass filter. This bandpass behavior ensures that only signals within a certain frequency range, typically the range where heartbeat sounds are most prominent, are amplified. Frequencies too low or too high are naturally cut off, helping reduce noise and irrelevant interference. Finally, C4, another coupling capacitor, is used at the output to remove the 4.5 voltage DC bias and pass only the amplified AC signal to the next stage. This prevents any DC voltage from affecting downstream components. So firstly, you have to on all the appliances. Then you have to make sure that the power supply is in independent mode, not series nor parallel. And afterwards, you adjust the voltage till it reaches 9 volts. Then you make sure that your function generator's output is turned on. Then you look at the oscilloscope's monitor, turn the knobs to adjust the size of the sine wave, and make sure it is in AC mode to get a better reading. So for stage 1, I put channel 1 to TP1 and channel 2 to TP2, and the function generator is connected there, and the power supply and ground. So we'll be setting our VPP as 200 millivolt, and that is our V in. And for our frequency here is 20 Hz, and for our V out it's 3.2 volts here. Then I will change the frequency to 100 Hz. And now my V out changes to 4.48 volts. This gives us a gain of 22.4, which is very close to the calculated 23 gain. And the AV here is 27. And in the table below, it shows other frequency recorded so that I can plot the graph. So 27 decibel is the highest point of the graph, and we want to find -3 decibel. and then we mark down to find that the lower frequency cutoff point is 20 Hz, while the higher frequency cutoff point is 1.1 kHz. So the bandwidth is just 1.1 k minus 20 Hz, which gives you 1080 Hz. The second stage of our circuit is an inverting amplifier, and it uses the second op-amp inside the IC TL072. This stage amplifies the signal further and inverts it, meaning that the output waveform is 180 degrees out of phase with the input. It uses a configuration called negative feedback, where part of the output is fed back to the inverting input through a resistor. This feedback stabilizes the op-amp's operation and keeps the gain predictable. Negative feedback is a key part of most amplifier designs. It reduces distortion, improves accuracy, and helps keep the signal clean. In our case, the gain is set by the ratio of two resistors, R4, the input resistor, P1, the feedback resistor, which is a trimmer potentiometer, and using the formula for an inverting amplifier gain equals to minus RF over Rin, and we get gain equals to minus P1 over R4, which will be 100k over minus 100k over 10k, which gives us minus 10. Because P1 is adjustable, we can fine-tune the gain. Increasing P1 increases gain, decreasing it lowers gain. This lets us match the signal level to what's needed in the next stages. Too little gain, and the signal is weak. Too much, and it clips. Since the op-amp runs on a single 9V power supply, we also need to shift the signal up to avoid cutting off the negative half. So, we bias the non-inverting input at 4.5 volts using R9 and R10 as a voltage divider, similar in stage 1. This allows the AC signal to swing both above and below 4.5 volt without being clipped. To summarize, this stage uses negative feedback for stable gain, inverts and amplifies the signal, and gives us manual gain control using P1. The signal leaves this stage ready to be filtered in stage 3. Channel 1 is connected to TP1 and channel 2 is connected to TP3. So now I'll be showing how the trimmer affects the sine wave, and I set the frequency to 1 kHz, while VP peak is still 200 mV. And as you can see, if the gain is too low, the signal stays too weak to hear. But if it's too high, the output hits the voltage limit and clips, causing distortion or saturation. So now I'll be changing the frequency to 200 Hz, and I'll try to trim until I get a perfect sine wave without any distortion or saturation. When I finally adjusted until I was satisfied, the VVP that I got was 4.68 voltage. Now, in stage 3, we use a second order low pass filter built using the IC2A op-amp, which is another part of TL072. This stage is meant to remove high frequency noise while keeping the lower frequency heartbeat signal. The filter is built using a silent key configuration, which is a stable and widely used method. It gives a sharper roll-off of minus 40 dB per decade, compared to just minus 20 decibel for a simple RC filter. The main components that define the filter are R7, R8, C6, and C7. They set the cutoff frequency using this formula. Fc equals 1 over 2 pi times square root of R7 times R8 times C6 times C7. Based on our actual resistor and capacitor values, the calculated cutoff frequency is around 1023 Hz. This means that frequency above 1 kHz are cut off, while important heartbeat signals typically below 150 Hz are preserved. Next, we have R11 and R12, which create a voltage divider to supply a 4.5 volt bias to the non-inverting input. This keeps the op-amp centered and allows the AC signal to swing both above and below 4.5 volt, avoiding clipping, just like earlier stages. The op-amp itself is configured for a unity gain, meaning the gain is 1, so it doesn't amplify, but acts as a buffer to preserve signal strength while filtering out unwanted noise. C5 blocks DC from stage 2 and C8 blocks DC at the output, so only a clean AC signals are passed to the next stage. In short, this stage keeps the signal clean, focus on the heartbeat range, and prepares it for final amplification in stage 4. For stage 3, this time the function gen is placed right before TP3, and for channel 1 is placed at TP3, and for channel 2 is placed at TP4. So here it shows that it's at 1k Hz frequency and the voltage is 3.28 volts. And I'll be changing it to 200 Hz. Now we see that the voltage has changed to 5 volts. And now we'll switch to 4k Hz. As for 4k Hz, it shows 400 millivolts. At 4k Hz, the signal is far beyond the filter's cutoff frequency, so it's heavily attenuated, reducing the output to just 400 millivolts. So this table shows the output voltage at different input frequencies. As we can see, the gain remains flat at low frequencies and then drops significantly after around 1k Hz, which confirms the expected low-pass filter behavior with a cutoff frequency close to 1k Hz, which matches our design. This table shows how the output voltage changes as we increase the frequency. At lower frequencies, the gain stays high and stable, close to 1, but after around 1k Hz, the gain begins to drop quickly. This confirms the low-pass filter behavior. The -3 dB point, which marks the cutoff frequency, occurs where the gain drops to about 0.707, and from our table, this happens around 1k Hz. Now, let's look at the frequency response curve to visualize this roll-off. So, in this case, our cutoff frequency is 900 Hz, and to calculate the bandwidth, we take 900 minus 0 equals to 900 Hz, which is similar to the cutoff frequency calculated around 1023 Hz. Stage 4 is the final amplification stage. Its job is to boost the filtered heartbeat signal enough to drive a speaker, so we can hear the sound clearly. This stage uses the LM386N1, which is an audio power amplifier designed for low applications. One advantage of the LM386 is that it has internal biasing and a level shifter, so we don't need to add voltage dividers or bias circuits like we did in earlier stages. This makes it very simple to use. The input signal is AC coupled into the LM386 through C13, which blocks any remaining DC offset and lets only the AC signal, the heartbeat, pass through. The gain of the LM386 can be set externally. In our case, we use a potentiometer P2 as a volume control. This allows users to adjust how loud the heartbeat sounds from the speaker. At the output, there's C15, which forms a Zobo network with a resistor. This network helps stabilize the amplifier by preventing oscillations and protecting against inductive loads, which is important since we are driving a speaker. Overall, this stage turns the small amplified signal into a clear, audible heartbeat sound, completing the signal path from the microphone to your ears. For this final test, I connected the oscilloscope probes to TP1 and TP5 to observe both the input and the final output of the system. The function generator and power supply were left untouched throughout. At TP1, we can see that the small heartbeat-like signal from the pre-amplifier stage. And at TP5, we observe the fully amplified output from the LM386N1 power amplifier. By adjusting trimmer P2, which acts as a volume control, the output voltage at TP5 gradually increases. I recorded a peak output of about 7.2 volt just before saturation occurs. This shows that our system is effectively amplifying a weak heartbeat signal from the microphone into a clear, strong audio signal, powerful enough to drive a speaker with minimal distortion. In conclusion, this project helped me understand how analog components work together to process weak biomedical signals like heartbeats. By designing, building, and testing each stage, from amplification to filtering to final output, I learned how precise component choices affect signal clarity and strength. This system shows how engineering principles can be applied to real-world healthcare tools, like electronic stethoscopes, and it's been a valuable hands-on experience that deepened both my circuit design skills and appreciation for biomedical applications. And with that, I would like to thank you for listening to the video. Goodbye.